In this lecture, we will be talking about electromagnetic wave, and I have made mention of this in previous lectures, where this is the energy that we totally dependent upon in making this whole concept of remote sensing a possibility. Now, electromagnetic wave, what is it? It is the energy that is reflected from the Earth's surface, the energy generated from the sun, as it hits the phenomena or the Earth's surface is reflected back. That reflected energy is sensed by various sensors on our satellite. So in this lecture, we'll be talking about the various um, portions, frequencies of the electromagnetic spectrum, those that we can see and those that we cannot see. How do we actually sense? The electromagnetic wave consists of a number of different uh, components. One being the most popular one is the visible light portion of the spectrum. That part of the spectrum, it helps us to see features. So whenever we see an object, it is because of the visible portion of the spectrum facilitates that. And there's also various portions called radio waves. There's heat. There's ultraviolet. X-rays are all parts and parcel of the electromagnetic energy. All forms of this energy travels at the speed of light, which is a known constant, 3 by 10 to the 8 miles per second. The type of energy being detected is characterized by its position in the spectrum. And as I said before, there are a number of different sensors that we can use to sense those different parts of the spectrum. The spectrum is commonly divided up into units of wavelength. So based upon its wavelength, we can categorize the reflected energy accordingly, and we can measure them in micrometers, which is 1 millionth of a meter. Electromagnetic radiation, because different objects return different types and amounts of electromagnetic radiation, the objective in remote sensing is to detect these differences and be able to use the appropriate instruments to detect those differences. In turn, it makes it possible for us to identify and also assess phenomena that exist in the real world and their conditions. And a lot of these reflective energy is also used indirectly to measure phenomena that we cannot actually put a device on. So we would infer based upon the image that we get, infer certain conditions, and you'll see that later on as we talk about more examples. This is what the electromagnetic spectrum looks like in a diagram form. Here in the middle, you are seeing the portion of the spectrum which is the visible portion, and it ranges from 0.4 micrometers to 0.7 micrometers. So very small range in terms of the frequency, its classification. And it's a small component of the spectrum that helps us to see features or see objects in the real world. Now, note here that as we go beyond the 0.7 micrometer, we are getting into the infrared. Beyond the infrared, we come to the microwave area, and then we have TV and radio frequencies. On the other side, if we go be less than the 0.4 micrometer, we will be in the ultraviolet, the X-ray, gamma rays. Now these are portions of the spectrum that we cannot see, but there's a large amount of reflected energy being reflected, and we want to be able to capture it or store it in the form of images. The electromagnetic radiation, it ranges from gamma rays, shortwave, high frequency and high energy content, to your passive radio waves, long wavelength, low frequencies, and low energy content. So there's a wide spectrum of frequencies being categorized in this spectrum. Here you see another representation of the spectrum, and the different areas or the bands that are used in capturing the different parts of the spectrum, how it is being used in other in applications. For example, a GIS application, you have the ability to sense different bands of frequencies and have them stored as separate layers in your GIS. You can turn them on and turn them off. So some of these bands could be in the visible portion of the spectrum, or also in the ultraviolet or infrared portion of the spectrum. You can also use satellite imageries, and the satellite imageries also get these different bands. But aerial photograph typically would use the visible portion of the spectrum. So I just wanted to show you in this slide here the different bands and how we can use this in other application. In particular, having these bands as separate layers in your application. Another diagram of the electromagnetic spectrum, but this diagram is showing the different frequencies and how they range in terms of from the visible portion of the spectrum. We have the near infrared, the mid infrared. There is also an area called the thermal infrared, and beyond that we can go beyond where there's a microwave, and again we have television and radio frequencies. We on the other side we have X-rays, gamma rays, cosmic rays, and all these we can use to be able to sense them in the form of data that we can use in other applications. So let's look at some examples of different portions of the spectrum. First one is your visible portion. It's a region in which the human eye is sensitive, meaning that it is the region in the spectrum that facilitates us to see objects. All right, so we're talking about trees, building, roads, whatever we can see with our human eye, we are actually using the visible portion of the spectrum. It ranges from 0.4 micrometer to 0.7 micrometer. Ultraviolet region has a shorter wavelength next to the visible blue region. All right, so be aware that the visible portion is the number one portion that we use on an everyday application. The other portion is your infrared portion. It cannot be seen directly with the human eye. It ranges from 0.7 micrometer to 0.8 micrometer. Longer than red rays in the visible portion, useful for penetrating hazy weather conditions. So if you are looking at mapping an area that has continuous cloud overcast, then you might be looking at using the infrared portion of the spectrum. Another portion of the spectrum is your thermal infrared portion. Cannot be detected by the human eye, nor by photographic film. It ranges from 0.8 micrometer to 14 micrometer, and the satellites that are able to sense the thermal infrared portion, they are equipped with electronic detectors cooled by that requires a lot of cooling, and they use liquid nitrogen to do that. But these electronic detectors are used to measure the thermal infrared portion of this. Another portion of the spectrum called the microwave portion, it has a very low intensity, and yes, if you did not know it, we do have microwave in the energy emitted from the sun, even though it's a low intensity, and we can use special sensors to capture those reflected energy that has microwave. The wavelength ranges from 1 millimeter to 1 meter, and it is useful for also penetrating hazy weather conditions. So microwave portion it is available, but however, because of its low intensity, the quality might not be. On this graph, it shows a comparison between the different bodies and the amount of energy emitted. So the sun, for example, here, the area on this curve is for the sun, it emits 6,000 degrees Kelvin. It's larger, a lot of energy is emitted from the sun when compared to that of the nominal temperature of the earth. So a large majority of the temperature of the sun is larger than that the amount of energy of that of the earth. But I also want to show you here this axis here, the x-axis is the wavelength, and our visible portion of the spectrum actually falls between this area here. So we can get a lot of the reflected energy from the sun. Okay, but if the sun was not there, the nominal temperature, we would not be able to sense that. So the highest amount of energy being reflected or captured in remote sensing occurs in the visible portion of the spectrum. Emission of energy from a black body under area under the curve represents the total amount of energy emitted. As I said before, the sun's highest energy levels are emitted at 0.5, which is around the area of the visible portion of the spectrum. You should also know that there is atmospheric windows. They are regions of the spectrum that are used for remote sensing, and these windows are consistent with the different portion of the spectrum. I'll show you in a while in the next slide. On this slide, you see the diagram of the atmospheric windows, and if you look carefully on the first part on the top of the diagram, we have the similar diagram, the similar graph as shown before, energy versus wavelength, and in this case here we are showing the sun's energy as shown in the previous diagram. The sun's energy and its wavelength, you see the ultraviolet portion, visible portion, infrared portion, and also the Earth's energy at 3000 degrees Kelvin. You see it's way down the side, and the wavelengths associated with them. Now, using this graph, we can identify some atmospheric windows for the sun's energy. Here, a similar diagram, the graph is drawn. You see transmission versus wavelength. Transmission, we see the ultraviolet portion of the spectrum, visible portion, infrared portion, and alongside that we see the windows that is available for them. Now, human eye can see visible portion of the spectrum. Using photographs, we can use visible and some infrared and ultraviolet portions of the spectrum to capture imagery. There's also thermal scanners that are used to capture this thermal portion of the spectrum. There are also multispectral scanners that can capture a wide variety of portions of the spectrum, including ultraviolet, visible, infrared, and even thermal region portion of the spectrum. On the other side of the diagram, you see where radar and microwave, it can be passive microwave. This is another window of the spectrum that we have sensors that capture the imagery associated with that. So it's very useful to understand these. It's another diagram, same sort of information, but it extends it further in terms of what sort of um, atmospheric transmission as it relates to different gases. So we can have water being sensed in this area here, carbon dioxide, water, and which one of the sensors are used to capture these phenomena. Very useful in terms of what do I want to capture in my imagery. Now, satellite imagery, typically all of the satellites would sweep the Earth's surface, and you have to understand that as the satellites sweeping the Earth's surface, the Earth is also orbiting on its axis. So one sweep in one direction does not mean that the next sweep is going to be the neighboring area. Usually it varies always. In this case here, sensors, a common satellite developed by the US, it's called Landsat. The SWOT width is 185 kilometers, meaning as the satellite going over the Earth's surface, it's actually capturing a width of 185 kilometers. When the imagery is captured by the sensor of the satellite, the raw data that's collected from the sensors is what we call continuous data. It's a space filling raster dataset where it mimics exactly, depending upon the resolution, exactly what is being displayed or in terms of the phenomena being mapped. So your original imagery is it's called a continuous dataset. However, we cannot do much with a continuous dataset other than just having it as a separate layer to overlay on your applications to make it a bit more realistic. What we have to do with the continuous data is define a set of classes. And once we define a set of classes based upon the values of the continuous data set, we would convert the continuous data into discrete data. Where a discrete data, there's a definite boundary between the features of that phenomena being investigated. In a continuous data set, there is no distinct boundary. And when it comes to changes in a particular phenomena, there's a gradual change at the boundary of that phenomena. In a discrete data set, there's a distinct boundary between the different classes. So you need to understand that, because it's great to have a continuous data set, but there's very little we can do. What we do is we make use of the discrete data set. Continuous data set, it's varied, and we can have two types as shown here. It can be a black and white panchromatic. You see some aerial imagery being displayed, and it's the different shades of white to black. We could also have a continuous data set which is multispectral, where we have more than two or more bands being displayed. This is much more realistic, and it mimics exactly what's being displayed in terms of the phenomena being captured. How do we view continuous images? What we do is we can view the different bands as separate data sets. Here you see band 1 being displayed, band 4 being displayed for the same area, band 5 being displayed. In band 4, what you notice here, yes, the water body shows up as being a pitch black color. However, in band 4, there is no distinction in terms of any white area shown here. However, in this map here in band 5, yes, the white area shows up. In band 1, the white area shows up, but it does not show up the water body. So this is just an example of where we can use panchromatic continuous images and emphasize the features that we want to emphasize, and have at our fingertips the other data set in the background, which can be used later on. How do we view images? Because there are a number of bands, especially in a multispectral image, we have the ability to mix and match these bands. And these bands can be looked upon as different layers, as shown here. We can have a blue layer, green layer, red layer, near infrared, and we have the other data set which is close to the infrared, short wave infrared layer. Now, each one of these layers have their specific colors, and as shown here, using the basic primary colors, we can mix and match them. We have band 4, 3, and band 2. When viewed together, this is the resultant map. In this map, you can see the urban areas showing up in a white magenta color, the water bodies showing up in a dark blue color, roadways showing up as white, and other features showing up, probably vegetation, as a false color, red. If I again mix up the bands, so I do 4, 5, and 3 from the different layers, I get a different imagery. We have blue, mauve, pink color showing up. The water body is still dark and distinct. The road shows up as red, and the other areas shows up at different hues, values in terms of green. And if I again mix up the bands, band 1, 2, and 3, I get another image which shows up the urban areas more distinctively. The water body is not so distinct, and the vegetation area is dark. Okay, another example of band combinations is one shown in this slide. When you change and mix up the bands, the features become a bit more obvious. In this diagram here, you see an image of an area, and that image was created using bands 2, 3, and 1, which is red, green, blue. I want to focus your attention in this area here where we are looking at the vegetation. If I should mix up the bands again, change up the combination to bands 4, 3, and 2, the vegetation shows up in green. If you focus your attention on this urban area here, change on the band combination would result to using bands 4, 5, and 3, it becomes a bit more distinct, the urban areas. So the benefit of band combination is to make the features become, or the phenomena become much more obvious. Very useful in terms of identifying or making clear what exactly I'm interested in looking at. Now, having the imagery in our system from the satellite, remember the satellite is going around the Earth's surface and it's capturing a large area. For example, I said earlier on, Landsat, the SWAT width is 185 kilometers. The raw imagery has to be georeferenced, has to have a reference. the raw imagery does not come with any reference. So what is required is that the ground receiving station would do some georeferencing or defining the reference system for the raw data. So if this is my area being scanned, that area is the entire US. Based upon the raw imagery, it needs to be georeferenced or coordinate system need to be defined. And how is that done? It's using, again, looking at the individual pixels, location in the imagery of your pixels, the ground control information of points that you have a rough idea where it is. Because remember, at this high level, it's very difficult to pinpoint, exactly, but rough estimates of ground control is going to be adequate. And it. Now, once you determine the X and Y coordinate, once you use the raw imagery, what the system does, the ground receiving station does, is define real world coordinate system for it. And what if they can identify the area where the ground controls are, what they will do is do a resampling and convert the entire image into real world coordinate system. All right, as you can see here, the coordinates at this point is as defined. It has a line of longitude and latitude. Ground control is very, very important. Raw data needs ground control, and how do we do that? We would identify these ground control on my raw data. Then the system would take the ground control that I would type in for these ground control and then do a transformation. These measured ground control are used to correct for the entire image. And there are a number of transformations that is available in your remote sensing software. Now, once it does that, it takes the ground control of where the points you identify as being ground control and has a coordinate system, has numbers, X, Y, and Z values. It does the resampling, and a new image is resampled. This slide shows you what a discrete dataset looks like. As I said earlier on, continuous dataset is not readily easily used, so we have to define the continuous data into a set of categories, and those categories define the theme of our image. It deals with categorical information about an area used and created by analytical operations used to extract information from multispectral images. Now, once we define those categories of data within a classified image, we would want to do some additional processing. Here is an example of a classified or an image that was defined in terms of different classes of information. It's the same image that we looked at, but what is obvious is that there's a definite boundary between different categories. So they're all polygons, and if we want, we can classify that. We can determine the area of these polygons. We can determine we could do overlaying of other data sets onto this and find suitable areas in a GIS environment. So it's very, very useful. Each pixel contains a value from that class, those classifications. Each class value is associated with a specific color. I can change the color in the attribute table, change the number, and that number has an associated color. We could also do things like each class can have an associated attribute. Each attribute can be added on, more fields added on to that table. We could put the name, color, we could add more fields to it. And this is what it looks like in terms of the classified data and the various fields that is added on. Pay particular attention here to the class names. Each one of these categories, there are 15 categories defined. The users give it a specific name, and it gives the area in hectares, acres, etc. Now, once we have this imagery that is classified into categories, we would typically start digitizing features. We can vectorize the data. For example, here this is an image, raster data set, use that as a background where we can draw out the features. This pond area, the other pond area, and then the roads. So this is raster data, and this is all vector data. Where we can also, this is new data set that is captured with reference to the raster data set. Very useful to in other applications, for example in GIS. We will be capturing whatever we see here, point lines and polygons. Your vector data, once we have our vector data, point line and polygons, then we can add attributes associated with these point line and polygons. So in this slide here, you see for these point line and polygons, we have the area, the perimeter, and other field that can be added on for further analysis. Okay, this concludes our talk with regard to electromagnetic spectrum and how we use the band combination, etc. Please download the PowerPoint, the notes page, go over the material, make sure that you understand it. We'll continue with our next lecture.